Okay, we get to capitalize on two ideas here. One is logarithm laws that you remember from your algebra or pre-calculus class. We'll see some great benefits to those. And second is how to differentiate logarithmic functions. Okay, so we're gonna put those two concepts together to look at something called logarithmic differentiation. Logarithmic differentiation. So the instructions for something like this, typically, you might usually get a hint, or you're lucky to get a hint. And it might be something like use logarithmic differentiation. Use logarithmic differentiation to find the derivative. So it's important to know what logarithmic differentiation is if you're going to use it. And in fact, it can make finding derivatives much simpler. Even though the result might look messy in the end, it'll be much easier than using maybe some other rules. So let's start with using logarithmic differentiation to differentiate y equals x to the x power. So this is an interesting function because a power function is x to a constant power. So this is not a power function. We can't use the power rule, and you might be tempted to do that. The power rule is where you drop the exponent down to become the coefficient, and you lower the exponent by 1. It's not a power function. You can't do that. Furthermore, an exponential function, which is very similar but different, an exponential function is a constant to the x power. This is not an exponential function either. So we can't use the derivative of an exponential function to differentiate this. But we can use logarithmic differentiation to do this. And so when you start any logarithmic differentiation problem, when you start any of them, you begin by take the natural log of both sides, okay? And that's before you do the derivative, because that's going to allow you to rewrite what the expression on the right-hand side using logarithm laws, and then you can differentiate to solve for, in this case, dy dx to get the derivative. So let's see how this works on this pretty simple function. All right, so let's take the natural log of both sides, resulting in the natural log of y equals the natural log of x to the x power. Now you're going to need to know your logarithm laws, and I will certainly be demonstrating examples of all of them in this video, but if you need to go back and refresh on those, make sure to do that. All right, so the left side's no problem. The left side is just the natural log of y. The right side can be rewritten, and this is when you might want to use logarithmic differentiation, is when you see stuff on the right side that logarithm laws would work very nicely on. And so since we've got a power, the logarithm law tells us that the exponent of the argument turns into a coefficient on the log. And so this is not calculus, this is just a logarithm law that allows us to rewrite this as x times the natural log of the x is all that's left in your argument. So it's x times the natural log of x. And so that's kind of a cool thing to happen here. Now what we can do is, after we've implemented the logarithm law, so let's write out some steps here. What did we do? From step 1 to step 2, we took the natural log of both sides, right? That's common to every logarithmic differentiation problem that you're going to work. Then the next thing you're going to do from step 2 to step 3 is you're going to implement the log laws. Now that you've got a logarithm, use the log laws. Okay? And we've done that. Now, after you've rewritten the equation using those two concepts, the next step is now you're going to differentiate. Okay? Differentiate. Okay, so let's see what happens here. The derivative of the natural log of y, well, that's 1 over y. But since y is a function of x and we're differentiating with respect to x, let's actually go ahead and write in what we're doing here. Let's go ahead and write the derivative of the left side and the derivative of the right side, okay? That doesn't hurt anything. So now we're differentiating this function with respect to x, which is 1 over y, but because of the chain rule, we have to multiply by the derivative of the inner function y, which is dy dx. On the right side, it's all a function of x, so no chain rule here, luckily, but we do have a product, so we have to use the product rule. So I'll do the derivative of x, which is 1, so I'm not going to write that. The derivative of x is 1 times the second function, natural log of x, so that's just natural log of x, plus the first function, x, times the derivative of the natural log function, which is 1 over x. So we end up with, I'm going to do two things at once here. We're trying to solve for dy dx. So I'm going to multiply both sides by y, right? To get rid of the 1 over y, I'll multiply both sides by y. So on the left side, I'm going to have y times the natural log of x plus x times 1 over x is 1. Now there's a reason I did not distribute my y, okay? We want our final answer to be all in terms of x, and we have this y involved. This part's always going to be the same when you do logarithmic differentiation. You can imagine that if the left side starts as y, then you're always going to get the natural log of y when you do the logarithm. If you always have the natural log of y, then you're always going to end up with 1 over y dy dx when you differentiate. Thus, solving for dy dx is always going to result in multiplying both sides by y. Sometimes y is a really nasty looking function, and you don't want to distribute it to all of the terms on the right side. So it's very common to leave the y out here. Now you can't leave that in your final answer, but if you distribute it and you go back to write everything in terms of x, if y is really nasty function, you're going to have to write that nasty function multiple times. Okay. The next example will illustrate that a little better. So what we're going to do to put this all in terms of x, well, y is just x to the x power. So I'm going to replace this y with x to the x power. So it's very interesting that the derivative of x to the x power is x to the x power times the quantity natural log of x plus 1. But you can see how simple that was to do if you rewrote the equation using logarithm properties first and then use implicit differentiation to solve for dy dx. So let's do another example where the function is much messier. And we can review the logarithm laws in more detail, and we can practice with some other derivatives as well. So use logarithmic differentiation. By the way, I typically try to put myself in your shoes if you're taking notes. So that's why I rewrite the instructions every time, because if you're taking notes, I assume you're probably having to rewrite the instructions. So that's why I do this. So use logarithmic differentiation to find the derivative of, and I'm using slightly different sentence structure here now in notation. So the derivative with respect to x of, let's say, e to the x times the square root of x times the quantity x minus 1 to the 3/4 power. Boy, that's nasty, right? But we want to find the derivative of this thing. Now, if we weren't told to use logarithmic differentiation, you might not ever think of it. But why is it a good candidate? Well, it's a good candidate because you've got lots of products. You've got an exponent here. The square root of x is also an exponent. We'll review that in a second. So you can use logarithm laws to rewrite this very nicely. Not nicely, but better than this for differentiation. If you don't use logarithmic differentiation, you're going to have to use the product rule in addition to the chain rule and power rule and all these other rules. So let's get into how to do this using logarithmic differentiation. So what we're going to do is, let's use a different color. Let's name this function y, right? So why don't we call it y? So let y equal e to the x times the square root of x times x minus 1 to the 3/4 power, okay? And you remember the first step of logarithmic differentiation? You don't differentiate to begin with. You introduce a logarithm so that you can use logarithm laws, and then once you've got that, you differentiate. So what we're going to do is we're going to take the natural log of both sides. So on the left side, we're going to have the natural log of y, and on the right side, we'll have the natural log of all of this. E to the x times the square root of x times x minus 1 to the 3/4 power. Okay? And so you can see, again, I mentioned it last time, you're always going to have this natural log of y on the left side when you're dealing with functions. So now we have to clean all of this up using logarithm laws. So we've got the natural log of y equals, and I've got a product of 3 factors here. So I can split this to be a natural log of the first factor, e to the x, plus a natural log of the second factor, the square root of x. Remember, multiplication turns into addition when you're expanding logarithms. Furthermore, the square root of x is better thought of as x to the 1/2 when dealing with logarithm laws, because logarithm laws tell us what to do with this exponent. So the square root of x is the same thing as x to the 1/2. And then I've got plus the natural log of my last factor, x minus 1 to the 3/4 power. Okay? And unlike the last example, we still have more work to do here. You can see we've got several things going on. I've got an exponent here and I've got an exponent here. You can even say I have an exponent here. But we need to simplify this further. Continue using the log laws to their fullest extent. So now we've got the natural log of y. You don't need the parentheses there if you don't want them. Now the natural log of e to the x, since this is base e, the natural log and the e cancel and just give you x. Okay, you may want to review that if you don't remember it. But the natural log of e to a power is always just the power. Okay. Plus, over here, the logarithm law is going to turn the exponent of 1/2 into a coefficient of 1/2. So now we've just got 1/2 times the natural log of x. Plus, similarly, this exponent is going to turn into a coefficient. So we get 3/4 times the natural log of, in this case, x minus 1. Okay? Just using log properties, no calculus so far. But now we can't go any further. We can't use logarithm laws any further. So now let's differentiate both sides. And so here's the cool thing about this current derivative that we're doing on both sides. Rather than doing a derivative of a product of 3 factors using a horrendous product rule, we're going to do a derivative of a sum of 3 summands. All right? That's much easier because you can differentiate these independently and just add it all together. There's no special rule that you have to use like the product rule. Okay? So let's get down to it. We already know that the derivative of natural log of y is 1 over y times dy dx because of the chain rule. Been through that already. Equals, and over here on the right side, everything is in terms of x. So they're simple derivatives. The derivative of x is 1 plus 1/2 times the natural log of x. Well, that's just 1/2 times the derivative of the natural log of x is 1/2 times 1 over x. Plus 3/4 times the derivative of the natural log of x minus 1. We have to use the chain rule here. So the derivative of the natural log part is 1 over x minus 1 times the derivative of the inside x minus 1. Well, the derivative of x is 1. The derivative of negative 1 is 0. So in fact, the derivative of the inside just ends up being 1. Okay? So now we're gonna do multiple things at once again. Pretty simple ideas here. We're trying to figure out what dy dx is. Because remember, we want to differentiate this y function. We called it y. So the dy dx will be the derivative of this massive function here. So to get dy dx by itself, we're going to multiply both sides by y. We've seen this once, so now we're going to take advantage of it. Rather than writing just y here, I know that I want it all in terms of x. Take some time and write that out if you want to. But I know y is all of this. So I'm going to multiply both sides by y, which is all of that. So in the last example, we actually wrote the step where we wrote y here times all of the other stuff that's over here, right? But now we know that that's pretty redundant, and there's already a lot of writing. So if we can eliminate that simple step of writing y times everything, and then writing one more step where we replace y with its definition, that's a good thing. Okay, so now we're just going to clean up what we have here on the right side, yes? We're multiplying the entire right side here by y. So that's what's going to go in the brackets. So I've got 1 plus multiplying the two fractions, I get 1 over 2x, plus multiplying the three fractions, I get 3 over 4 times the quantity x minus 1. And this is the derivative of this massive product of three factors. No product rule involved, just logarithmic differentiation. Of course, implied in that is some implicit differentiation, some chain rule, some things like that, some logarithm laws, but really good stuff, and I hope you see the benefit of it.